Good morning to all. So here is the first question. How many of you could establish this? The closure of this ball is the closed ball. Those who could get, then say yes. There are only two. Okay. So the excluding this two. Okay, I'll ask the question. So how many of you at least tried and could not get? Okay, even that is very limited. Okay, so we'll quickly go through. Maybe I'll ask one of them. Yeah, Chetan, what is the difficulty?
Sir, if we take a sequence xn, so mod of norm of xn minus norm of x is less than epsilon. So norm of x is less than norm of xn plus epsilon. So because norm of xn is also less than r, then norm of x is less than r plus epsilon. Then norm of epsilon is arbitrary. So norm of x is less than r, so it is belonging to also in bx comma r. Closure of bx. Yes.
Okay, so which part you are saying is easy? Which part you could get?
We get this limit, take any limit point which inside in bx comma r.
No, there are closed and open. You have to say that way, then only you will be able to understand. So the left hand side is subset of right hand side, or right hand side is subset of left hand side?
Left hand side is a subset of right hand side.
Okay. So do you all agree at least? So there are other people I will ask anyway. How many of you clear that this is true? Yeah, how many of you are clear about this? Okay. So the way that to go ahead is the following, that you can go in two things. Number one, I'm just writing the steps. Can you see that? Suppose if I have is this clear? I'm clearing it out. Is this clear? B closed XR is a closed set. How is that? I will not write everything. I'll leave it for your discussion. How do you show that it is a closed set? Take a sequence here xn which is converging to some x, and you have to prove that x is here. What is the meaning of saying that limit point x is here? When let us not take x ans. So ans is a sequence in bxr which is converging to a. I want to prove that a is here. So for that I need to prove that distance between a and x is less than or equal to r. That's all I need to prove. But what you know is the distance between an and x is less than or equal to r. That much you know. And you have to go back to your basic metric space information. Either you use epsilon delta definition to conclude that, or if you know the result, you can use that. or if you have difficulty, a much more intermediate step. Can you see that this is a closed set? Now it is saying that you take an xn, an which is converging to a, and you need to prove that a is in this set, which is essentially proving I need to prove norm of a is less than or equal to r. But I know that norm of ans are less than or equal to r. So you can start with, you want to estimate norm a and see that what you can do. Norm of a, either you use this fact, so norm of a is what you need to estimate, and this you can add and subtract ans. I'm doing directly from the first principle. Okay. And I know that this is converging, so I can make this to be less than whatever epsilon that you want. And what can you say about this? These are all less than r because they are coming from this close, less than or equal to, in fact. This is less than. So this norm a is less than r plus epsilon for every epsilon, and hence its epsilon is arbitrary. You get norm of a is less than or equal to r. That's one way of proving. Once this is closed, this is bxr is nothing but x plus b0r. So that's also a closed set. Okay. Okay, so this is a closed set. And next thing that I want you to notice, if you know the definition of closed set, what is this set? If you have learned the metric space, you might have studied that this is the smallest closed set containing bxr, right? Containing the open xr. Okay. Now this inclusion is immediate. The moment this left hand side, this is the smallest closed set containing bxr, and this is some closed set. Here also bxr is subset. So smallest closed set has to be smaller than arbitrary closed set containing bxr, and so this is immediate. Okay. So what is the next part that you need to show that bxr is contained in bxr closure? Okay. Yeah, now I'll ask, yeah, Tanu.
Yes, sir. Now we have to just prove, because B, we know that that closed ball is we have same, that y is the element if and only norm of y minus x is less or equal to r.
Yes.
So that means just we have to prove that for such y, such that norm of y minus x equal to r, it belongs to the closure of the open ball.
Okay, correct.
So now that if you take any point from that, let's take y. Okay. So we can find y in sequence inside from the open ball, because open ball will be convex. So that's why we can have that sequence actually. In vector space, we can have convex set.
Okay. So did we define convex set?
I think not, sir.
Okay. Okay. But okay. So is that point clear? What he's saying? So take a y from the left hand side, and you have to show that that is in the right hand side. So there are many ways. One is you say that. One way is that you get a sequence yn from bxr which is converging to y, and that proves y is a limit point of bxr, and hence y belongs to the closure of bxr. That's one way that you can try, and he is using the convexity of this one, this ball. That's one way. And there is a even more straight definition. When you say that this, what is the closure of the bxr? If I want to show that y is in the closure of bxr, can I say the following, that if you give me for every epsilon, if you give me any epsilon positive, if I consider ball centered at y epsilon, and if it intersects with bxr, then also it proves the same. How many of you agree this? I want to say is the y is a limit point of open ball bxr, which means that around that point, if you take any open ball, it has some point here in this ball. That intersection is non-empty. Now, if you understand geometrically, that's easy. That's what he is saying in terms of convexity also. So so this is something like bxr. So this is x and this is the distance r, and you are taking on the boundary. So I take another color, say. So this is an element y. Okay, that's what we are thinking. It is belongs to closed bxr. All we are saying is that if I take any ball around this, I need to produce an element inside this bxr. So the choice is clear that I need to use this line to create a point. So maybe this is the point that I will use, this red point. And hence he is using the convexity. So just maybe we don't need actually even convexity. You can check without convexity also. Without using the explicit notion of convexity, we can say that. What is the line joining these 2 points? The line joining these 2 points, or any point on this line, is given by this expression. What is the expression? There are 2 expressions, whichever you like. So it is 1 minus t times of x plus t times of y. So if I take t to be 0, it's x, and if I take t to be 1, it reaches y, and all the points in between are things. So it is actually t is so the moment if I so the convexity definition is this. Anyway, we'll come back to that anyway. So this is a line. Any point on this line joining x and y is given by this expression. It's called a convex combination. One can also rewrite this as this is equivalent to writing separate terms. So x plus t times y minus x. These are both expressions. And in case if I drop the t being 0 or 1, can you see that it is actually inside the ball? Inside which ball? bxr. What do I need to check? Let's say this is a point, call it as what is it, yt. I'm getting some kind of sequence yt. It is depending on t, no? So I'm writing it as yt, and see that yt belongs to bxr. Is this clear? All I need to check is yt minus x norm should be less than or equal to strictly less than r. So yt minus x is t times y minus x, and norm of y minus x, I know that it is from this expression is strictly less than or equal to r, but t is strictly less than 1, so it has to be strictly less than r. So this gives you. Now I'll ask the question that yt, does yt belongs to this next ball? Does this belongs to by epsilon? Does yt belongs to this ball? Answer is straightforward. not necessary for all t, because look at the green. As long as if I take the red point is the one yt, if it is inside this green ball, it will be inside this by epsilon. Otherwise, it will be outside. So I need to choose appropriate t. All I need is some. I need to show that this intersection is non-empty, right? So I can should I be able to choose a t so that what you want? That's easy. Let's say that so such a yt exists. I need to find out what is the t. So if at all I want this, let us work reverse and then see what kind of t I need to choose. So what is the norm of yt minus y? So I am checking yt minus y. If this happens to be less than epsilon, then I am through. But t is in my hand. I'm trying to find out t. What kind of t will give me it is less than epsilon. But just substitute this expression. What is yt minus y? Now in this case, look at these two expressions are same. So yt minus y will be can somebody tell? 1 minus t times of x plus ty minus yt. The whole thing minus yt you have to put. So it is 1 minus t times of x plus ty minus yt. Okay. So the way that I wrote it is y minus yt or yt minus y are same. Did I wrote it correctly? Yeah. No. So it is yt minus y. So this is the yt minus y. And see that if you simplify, you get 1 minus t times of this x, and this will be 1 minus t times of minus y. So it is, can you see this? I don't need to put a modulus because t is between 0 and 1 is what I was actually looking at. I want this to be less than epsilon, but norm of x minus y, I already know it is. I started y from closed ball, so it is less than or equal to r. So it is less than or equal to 1 minus t times of r. And I want this to be less than epsilon. So can I choose a t satisfying this? Okay, if you know how to choose this, can you tell Datta what will be the t? Of course, we already done. You can do that.
1 minus r by epsilon.
No, simplification is 1. What kind of t? Will you take t to be close to 1 or close to 0?
Close to
Close to
1.
1. Yeah, that's what the ball also, the picture also tells you. Okay, you can choose a t. Okay. So maybe you can take t to be some, if you want, some n minus 1 by n kind of type, and then you can write. A reason for me writing t equal to n minus 1 by n, which you can make it as close as 1. The reason is that then yt you can write it as yn. Depends on n. No? So substitute and see what do you get. It is, so it's something like 1 by n. So simplify. Okay, simplify and then and get n. Okay, so you will get n, the choice of n. That's it. So that proves. So I'm leaving this calculation for you to go ahead. Substitute this 1 minus t times. So that is the kind of n that you will choose. So if I choose n to be like this, then the yt will be there in this ball as well as this ball. Is this clear? If it is clear, then say yes. Then we'll. Namachivayam, you also use the essentially same idea.
Yes, sir. Yes, sir.
Tanu, it is same?
Yes, sir.
Yeah. So we are using this. Anyway, this brought us to this this definition, what is called a subset is convex. This is nothing to do with a subset A of a nonlinear space X is convex. In fact, to speak this, you don't need even nonlinear space. The vector space is enough. Is convex if, what is the definition? If X and Y are in A, then the convex combination is also inside. That means then for every T belongs to close 0, 1, 1 minus T times of X plus T times of Y also belongs to. Yeah, check, is this the definition that you learned or some modification is needed? So a set is said to be convex if you give me X and give you Y, and if I join the line has to be completely inside. So this is a convex set. This is a convex set. This is a convex set. The planes at least. But more general example is are you able to see this? Say take 2 points A and B in BXR and consider this, and you have to show that that is also here. Just go through the proof. So take A and B. So A and B belongs to this BXR. And you need to say that 1 minus 1 minus T times of A plus T times of B also belongs to this set. That's what you need to show. Which means I need to check this. I need to see if I want to say that this element is here, I will check this. Minus this X. This, if I show that it is less than R, I am done. At this kind of stage, what I will do? I know that A is in BXR and B is also in BXR. So somehow I know how to estimate A minus X. And somehow I know how to estimate B minus X. So what is the way to go ahead? This is a standard thing. Yeah, what you will do with the X? How many of you know? Yeah. So Srujana?
So add plus tx and minus tx.
Right. So you will split X into that. That's it. So you will write this as X itself. I can write it as Tx plus 1 minus T times of X. Right. Which is same as what you said. Correct. Okay. Now you can combine them. So combine these terms and other term. Oh. No. 1 minus T times you combine and T times, yeah, this you combine them and and estimate. So T will come out and then B minus A. And so I leave it as. So you can check that this is less than or equal to, strictly less than R. So that proves it's a convex set. So one more quick example is, can you see that the same argument will give you this also? So this is also a convex set. Is every subspace a convex set? Yes or no? Remember, all that we are asking is 1 minus T times of A plus T times of B is a convex combination. But subspace linear combination itself is there. So we will get that also. Right. So these are the typical convex sets. We'll use again and again. Okay, this is a digression. So we have proved BXR is actually, so the both inclusions gave you this information. Closure of the open ball is the closed ball. And this is in general not true in metric space. This is something extra that we got in this discussion. Okay. I will go ahead. Yeah, if you have any doubts or any comment that you want to make. Is a line segment a convex set in plane? Yes. Okay. So there is a geometric thing connected. But the balls, what we are saying, you can think of it is, it's not just the plane geometry that you have. So if I consider the unit ball in C of X, C of 0, 1, and that is also convex. That's what it says. Okay. Things. We have also defined sequences using the metric and convergence of sequence. We also said what is a Cauchy sequence. And if every Cauchy sequence converges, we said that it is a complete space called Banach space. And every converging sequence is also Cauchy. Is that immediate? The nonlinear space also. Like as in the case of real numbers, every converging sequence is Cauchy. Okay. There's some extra thing. So I'm asking you to check that. Only thing is this, the proof is essentially same, excluding the modulus you will be replacing by the norm. What about boundedness? Does every converging sequence is bounded? Just look at it is the same. You will use the same idea, your real numbers type. What about does Cauchy sequence also bounded? Does every Cauchy sequence is bounded? Same. Okay, the same proof you can use. So this is also bounded. Right. Okay. The another important notion in the nonlinear space is the following, which is called equivalent of norms. Maybe I'll call it as equivalent norms. So what is this equivalent norms? On a single space, you have two different norms, and I want to compare them. So on X, this is a non-linear space with respect to one norm, and this is also another, the same space with a different norm. These are non-linear spaces. So on single vector space, if I have two different norms and I want to compare them and get some connection among them, so you say that norm 1 and norm 2 are equivalent these are equivalent norms. What we need is that the norms gives you a metric, and matrix induces a topology, and those two topologies are same. Okay, so the induced topology. Okay. So take a minute in understanding. The moment you give a norm, it gives you a metric, and from the metric you can actually create a topology. So starting from one norm you get a topology, starting from two norm also you get a topology, but finally both of them creates the same topology. So as a topological space, these two non-linear spaces are not different, they are same. Okay, so that's the definition of equivalent norm. Now, based on this is the working definition for us. Have you come across this equivalent of metrics also? Equivalent metric. Okay, so if you have come across, okay, Datta has not come across. So if you have come across equivalent metric, it is saying the same. If the norms are equivalent, the induced metrics are also equivalent, and hence the induced topologies are equivalent. We'll go to that in a minute. Right. So what I want to say, next thing is we want to quickly look at the following. That is, there is an easy way to check in the case of nonlinear spaces when two norms are equivalent. That is the following. So if you can say that norm 1 sorry. So norm 1 and norm 2 are equivalent if and only if there exist A and B, of course positive numbers, such that the following happens. That is norm of norm of X with one norm is less than or equal to norm of the two norm, which is less than or equal to some B times. So this happens for all X in the space. So best way to even rewrite. Okay. So we want to say this. So I say that two norms are equivalent on X on a single vector space if they induce the same topology is the original definition. But in the case of nonlinear space, it's easier to check if I could get the following, that if I can find out A and B such that for all x in x, A times norm x1 is less than or equal to norm x with respect to the second norm, which is less than or equal to B times norm of x with respect to the first norm. Okay. So if I want to prove, we'll prove this statement. It's not very difficult once you know what it means. When you say that, how do you say that two topologies are actually equal? That's what we need to establish. What are the ways to say that the two topologies are same? I gave you topology tau1 and another topology tau2. I want to say that these two topologies are same. Yeah, Vijush?
Yes, sir.
Yeah.
Sir, two topologies are same. If take some open set in one topologies, and it will be inside in some open set on the second topology.
That's it. If you take an open set in one of the topology, you should say that it is also open in the other topology. Okay. And the way that you prove something is open. So if you take a open set in one topology, you want to say that it is open in another topology. But the way to prove that is open in another topology is that if you give any point in that set, I give a open set containing that point, which is contained in that set. What you call it as a basic open set. See, in our case, we have already established what are the basic open sets. What are the open sets? If you could recollect, we have defined a basis. Do you remember? This is all collection of all BXRs. Okay. All our typical balls, they form basic open sets. But since we have two metrics, maybe I will call it as B1 for this, and I will use B2 for the second one. Okay, this form a basis. So if I start with one open set, I need to check it is actually open with respect to other thing, which is same as saying that give you any point in that, I should be able to find out another open set, which is here. Maybe I'll write it so it will be. So if so, consider say B1, and remember all these sets are also equivalent to writing this. This we have seen. This is same as B0R. So even if I prove for 0R also, fine. So suppose if I give you an open set. So I'll start with this. So BXR. So this is actually open in D1 matrix. What do you mean by D1 matrix? It is the metric which is coming from the first norm. Since it is, since these norms are equivalent, this set has to be, so since it is equivalent, this B1 of XR is, since norm 1 and norm 2 are equivalent, this is open in D2 metric also, right? So this is also open in D2 metric. How do I say that this is open? In fact, if you give me any point here, I'll be able to find out an open set sitting inside and then containing that point. Okay. Now what I do, this can I just for the sake of easiness, I will do the 0R, and then I urge you to check what happens to general. The proof is essentially same. now what it says now, this is open in D2. That means 0 is an interior point. So 0 belongs to B10R, and it is also open in D2. So what do I get? So there exists a radius S such that this ball centered at 0 of some radius S, but with respect to the second metric will be here, and which will be sitting inside this. Do you all agree this statement? Once you understand this, then things are done. So those who have not done topology, even metric topology is enough in this discussion. If you have done metric space reanalysis course, it is there. I'm saying that B10R, this is open. We are saying that this one is open in this metric, and in particular 0 has to be an interior point. So for 0, I should get a basic open set which is of the form B20S, which is contained in that B10R. So this is what I get. What is the meaning of that? I just rewrite this meaning what it means. So if I take any x from this place, okay. So if I take any x, let's say y, I'm calling. So if y belongs to this ball, what is the meaning of that? If norm y is less than s in the second norm, that y is also here in the next set. That means it says that the y, one norm of y is less than r, right? Correct. If you understood this step, then say yes, and after that, then there is almost nothing to do, only some modifications. Now I exploit the nonlinear space structure to say the following, that is it same as saying that if you accept this? There are various ways of reaching this. Okay, it is just the kind of manipulations. Right. Good. Now, so can I'm rewriting, but one can also do in a different form. So can I say that this is also equivalent to saying that S into Y by S, this norm is less than R. Remember, I am trying to find out some connection between this norm and that norm. It is the same. I multiplied and divided by S is a positive number, remember. So I can do this. And this is actually equivalent to saying I will get mod S here, but that's also S, and I push it to the other side. Do you accept this? So if Y by S is less than 1 in 2 norm, then Y by S in 1 norm is less than R by S. So I can actually replace Y by S by some Z also. All it says is that it's true for, so if I norm Z this less than 1, can I say this in 2 norm, then norm Z in 1 norm is less than R by S. Good. Now things are clear now. So if at all, if I take a z in 2 norm with less than 1, then I can estimate the 1 norm. So always remember, this is the way that we go ahead. Is there any way to take any element? Can I make it inside the 1 ball? Of course, if the element is 0, then there is a problem. Excluding 0, I am leaving that part, which is, see, the inequality, is it immediate if the here? So this part, can you see that if x is 0, then inequality is true. So I'll assume x is non-zero. Then what is the way to bring inside the unit ball? This is a standard thing. So I start with any x in x, and the easy process we have done called normalizing. So if I consider this with respect to 2 norm, and then if I consider the 2 norm of this is going to be actually equal to 1, but I want it to be less than 1. So natural choice is this, and this will be less than 1. So what this gives you? So this whole thing is like a z now. So given any x non-zero, I can do this. So from the above estimate, it says that if I look at x by 2 times of this 1 norm has to be less than r by s. That's what it says. Now simplify and tell me what do you get. It says that, so if I take the norm, the numerator will have 1 norm. These 2 times norm x2 are all constant. I can push it out. So I get r by s, 2r by s times norm of x2. Okay. So do you see the constant? Remember what we are trying? We started with the definition if norm 1 and norm 2 are equivalent, and we need to produce a and b. Did we get anything? Maybe one side I got it, that if I take a equal to s by 2r, then it is a times norm x1 is less than norm x2. We got this. You all agree? Right. So can I get a B also? Say yes or no. Yes, all you need to do is you start from the other side. Consider B1, B20R is open in D2. And since norm 1 norm 2 are equivalent, it is B20R has to be open in D1. So swap the roles and you will get the other part also. So I leave that as an exercise. So and hence that proves that if 2 norms are equal, one part of the implication we have proved, if norm 1 and norm 2 are equivalent, then you have a and b such that this happens. Okay. Now, assuming the lower statement, we want to prove the upper statement. That is, if I can find out a and b such that for all x this inequality is true, I want to prove that norm 1 and norm 2 are equivalent. What do you mean by that? Norm 1 and norm 2 are equivalent. I want to prove both topologies are same. What are the ways of proving both topologies are same? Again, you can go back. If every open set here is also open there, is what we need to show. And is there any easy way to establish that? What is the map which is obviously continuous between the same space if the topologies are same? If I want to prove the topologies are same, what map if I prove continuous, I will get the topologies are same? Is my question clear? So I have x with the topology and tau 1 and y with tau 2. I want to say that tau 1 and tau 2 are same. So what is the map that I can think of which will help me to conclude that if at all there is a function f, if it is continuous, then inverse image of any open set in tau 2 has to be open in tau 1. But I want to say the every open set in tau 2 has to be a open set in tau 1. That means that inverse image should take that open set as it is. So what is the map? Yeah, Guru Prasad?
F of x is equal to x. Identity map.
Identity maps. Okay, consider the identity. Okay, so consider the identity map. So is this continuous? So if I prove that this is continuous, then what I prove is that tau 2 is contained in tau 1. And to prove the other way, I will prove identity map going from this to that. Or if I prove even homeomorphism, I am done. Okay. So we are trying to prove that identity. What is the map? It is I of x equal to x. It's a homeomorphism. Bijective is clear. 1, 1 and on to it is immediate because it's an identity map between the same spaces, by the way. Sorry. This has to be x. Not undefined space. So continuity, we need to show that. Is the map continuous? How do I check continuity? Remember this, though the topology we have written, it's actually coming from induced metric. So I will check what is I of x minus I of y in terms of distance, which is same as this now. But by definition, it is I of x is x. I am starting with in tau 2, so it is at 2 now. So can I get some estimate in terms of norm 1? Yeah, Vipanjana, do you have any easy estimate here?
So norm 2 is less than b into norm 1. So we
Yeah,
can
so
use
this
B.
you use the fact that these are
Equivalent.
this equivalent. So use that. So here I've written 2. So from here you will get b. So I know that this is actually less than b times this. And so I get the continuity of the map. In fact, it is Lipschitz continuous. And same thing with I inverse also. And that proves it is actually a homeomorphism. And that concludes the theorem. So what it concludes is the following. If norm 1 and norm 2 are equivalent, then in the case of nonlinear space, it's easy to check by finding two constants a and b such that a times norm x1 is less than or equal to norm x2 is less than or equal to b times norm x1. Somehow I can estimate one norm in constant multiples of the other norm.